Yeah, but so esida ke ngoku ne esilapha ke ngoku we wanted to calculate the binding energy when we remove a neutron. Hey, so now we need a mass defect. So a mass defect is change in m, which will now be equal to into zami ngathi azimanga kahle, ngathi akambanga. So we have a mass defect, which will be the mass of H2, right, which is this one, plus the mass. Wait, besithetha nge-n, now we are removing a neutron, right? I think lesingarepresenta ngo-n yabo kwenzela singazuyiphazamisa, because the mass will be different. So plus the mass of n, 1 there, and then minus intoni la atom ke ngoku la H3. So that should be our mass, and then change in m will be mass of your hydrogen, or your hydrogen by 2. If we come here, we do have 2 hydrogens, and then the 2 hydrogen is this one, which is 2.014102. 2.014102 U, 2.1014. Yes. And then now we have what? Mass of a neutron, and then is this one, which is 1.008665. So plus 1.008665 U, and then minus hydrogen by 3, which is hydrogen 3 is this one, 3.016, 3.016, and then 049. Can take it. So now let's see, what do we get? What do we get? What do we get? Ibethe kweli cala lam, so we have 2.0141102 plus 1.008665 minus 3.016049, and then ngithola u-0.006718 U, so that is the mass that I get. Danko. So now we know that the mass defect will actually be equal to the mass defect multiplied by 931.5 mega electron volt per C. So that's gonna be 0.006718 U multiplied by 931.5 MeV over a C, actually over a U. Over a U there. Yes, now sesifuna i-energy now. This should be energy. And ithi mass siyifumene in terms of U. So now this is binding energy. Then I get 6.258. Okay, we can use that 3, ne? But again, we want the units to match. remember that if we're saying that the energy will be mc squared, and then we're saying that the mass, now let's say we have, for example, 25u, and then we multiply by 3 times 10 raised to 8 meters per second. You see, these units and these units don't match. And if we take that 931.5 mv square, mv mega electron volts over u, this u will cancel that u. So that means, Miner, in order for us to use La 3, we need to have our mass in kilograms. Yes, it should be in kilograms. So that they will give us joules. Yes, so let's try something. Let's try something. So if you can take La U, we got 2U8, which is mass yethu, I mean the mass lane 0.006718. So that was 0.006718 U, right? So we know that our 1 U is actually 1.66054 times 10 to the minus 27 kilograms. I think you remember that number. So if you exactly. So if we wanted to use that C, would actually say 0.006718 multiplied by 1.66054 times 10 to the minus 27. And then now this will be in kilograms. And then we multiply by 3.0 multiplied by 10 raised to 6, right? Because that should be a million squared. So let me see what's gonna happen. So 0.006718 times 1.66054 times 10 to the minus 27. So this is minus 27, and then multiply by 3 into 3 times 10 raised to 8. It should be 3 times 10 raised to 8 many here. All squared. And then I get now 1.003996 times 10 to the minus 12 kilograms. So now these are the kilograms that I get. I mean, no, not the kilograms, because we are already calculating energy. So these will actually just be joules. So this is the energy in joules. Yes. So to see if this is true, you can reconvert from joules to what? Mega electron volts. So we can say how much mega electron volts is a joule. How much joules is 1 mega electron volt? So if you can come here, maybe try to search electron volt to joule. So 1 mega electron volt you see is equal to 1 point, and this constant we also had it. So 1 mega electron volt is equal to 1.60218. So 1 mega electron volt is equal to 1.60. Let me double check again. 1.60218. Then times 10 to the minus 13 to the minus 13 joules. That should be joules. Yes, those are joules. So now that means we can multiply this now. Can multiply the number that we get by what? 1 mega electron volt over 1.60218 times 10 to the minus 13 joules. So you know that this joule must cancel this joule. Let me see if I get something that makes sense. So answer divided by 1.60218 times 10 to the minus 13, and then I get 6.266 mega electron volts. Of which at first what we got, can you see? So that means, but for me it's better to just use this one because it's an easier number rather than when you are using the kilograms, because you'd have to convert using this guy. But it's also easy, by the way, it's also easy because after getting that thing in use, you just substitute 1.6605 times 10 to the minus 27. It will be automatically all of this to be kilograms, and then after that you multiply by the speed of light squared, and then you find your final answer now is 1 times 10 to the minus 12 in joules. So that's it. I think so too. So now, exactly. I mean, again, another thing is when you use this way, you get it in mega electron volt. You can easily change to joules still, because that's when now you will need to use this number. So in case they want it in joules, but most of time, I mean, they just say calculate. So anyways, just do the way you prefer. So I mean, you just convert it when they want it then in joules. And by the way, this one gives us very, very small numbers with negative exponents. So it's better to get a 6.266, which is just a normal number. Yes. So now from here, we are required again to remove a neutron. We removed a proton, right? And then we removed a neutron. Now we need to separate the remaining protons and neutrons. So if you check here, now we need to separate the remaining protons and neutrons are to be separated. Because remember now, after removing this using this equation, we used this equation, right? So that means we removed which guy? We removed this guy. So when we removed this guy, we are then left with this guy here. So that means now we are left with actually a 2,1H1. So we need to separate, because that means obviously we have one neutron and then we have one proton. Now we need to separate these ones according to the question. Makes sense, Mr. Ne? So now that means if H211. Now when we remove that, obviously we'll be left with 1 1 and 0 here, because let's see. And then the other one should be neutron, because it was a proton and a neutron. So that means separating. So we are left with 1 again here, 0 here, and then still 0 here, because I mean 1 plus this one will give us that 2, and then 0 plus this one will give us that 1, and that 0 plus 0, that means the 1 should be 1 somewhere here, because that is the number. Oh, not here, ne? Because I get with a neutron. Should we have 1 here? But either what? Just put one like this, ne? Like you mean like this? Should it be like this, Manner? Oh, you say in this age I should cancel here. Yeah, we are separating the proton and the neutron. Yes. So anyways, Mister, we know that don't think this should be difficult. We'll be left with one neutron and one proton, I it. So either way, we know that we just have one mass and one mass for each. So I don't think that should be difficult because we know that our mass defect will actually be the mass of the what of the proton and it plus the mass of the neutron, and then we subtract the what the mass of the atom, which is the total mass. Either way, just using understanding it. So and then you know that the mass of proton is that 1.00782 u, if I'm not mistaken. I think it should be something like that. 10 plus according to this, yes, 1.007825. Then neutron, that's 1.008665. So 1.008665 u, and then we minus the mass where they were combined. Now we should be, what should it be? Oh, we should come here, ne? So to H2, isn't it? Which is 2.014102. Because that was H2. So yeah, 2.014102 u. And then now we can actually calculate 1.007825 plus 1.008665 minus 2.014102, and then we get 0.002388 u. So after getting this, you see from here, if you want to get your answers in joules, you can convert now, since you know 1 u is equal to 1.66054 times 10 to the minus 27 kilograms. So otherwise, let's just continue like this. So we know that now energy will actually be the delta m c squared, where our c squared is equal to 931.5 mega electron volts per unit mass. Then our mass we've already found to be 0.002388. Just trying to fix that. 2388 u multiplied by 931.5, and then mega electron volts over u. Then can find our final answer there. And then I get an answer of 2.22 mega electron volts. So that's the answer that I get there. Tango. So from here, the question said the remaining proton and neutron are separated, and then from there, determine the energy required for each step. We have done. compare your results with the total binding energy of an alpha particle. Yayiva ke ngoku. Compare, it says now compare your results with the total binding energy of an alpha particle, right? So now let's first calculate a total binding energy using what we have found. So the total binding energy will actually, yes, let's add all of them. So firstly we got this 19, we got this 19.81 first. So we can take that 19.81 plus, secondly we got that 6.27, so 6.27. Thirdly we got this 2.22, then 19.81 plus 6.27 plus 2.22, so I get 28.3 mega electron volts. Now they are saying, the question was actually saying that we should compare your results with the total binding energy of an alpha particle. So now let's calculate the total binding energy. Total binding energy of an alpha particle. Without now separating, again we're just calculating the overall, because there those binding energy were to remove those one by one. Now we just want the total binding energy of an alpha particle, and we know that alpha particle consists of helium-4 and then 2 here, right? So now we know that these alpha particles, the number of protons is equal to 2 because it's that one here, and then we know that the number of neutrons is equal to 2, which is this one here. So now we know that the mass defect will actually be equal to protons plus neutrons minus the atom itself, which is helium. So now we have 2 times protons, which is 1.007825 U, plus 2 times neutrons. I forget this one for neutrons. This is 1.008665, 1.008665, ne? Now what about the mass of helium? That's the question. How do we... Oh, good, Mr. Good. Here is it, you are given. So that's 4.002603. 4.002603 U. So now let's see. That's 2 times 1.007825 plus 2 times 1.008665 minus 4.002603. So now I get 0.030377 U. So now from there we want to calculate the binding energy, which is equal to mass defect C squared, where our C squared will be 931.5 mega electron volt per U. And then now we take this number that we got here, which is 0.030377 U multiplied by 931.5 mega electron volts per 1 U, where this U will cancel that U. Then when I multiply those two, I get 28.3 mega electron volts, of which becomes the same as what we got here when we calculate it individually. Does it make sense? Yes, it does. Exactly. They are the same as expected. So they should be the same, actually. Yes. So we've done the comparison. What else? What else do they want from us? Calculate the power. No. Determine the amount of energy it takes to remove a neutron from a particle. Hey. Kwase kwanento endingayivisisi. What does that mean now? Or maybe that's what they want. Ne? So we are just removing the neutron straight from H4 because when we remove the neutron, remember we removed it from where? From where we already had removed the proton, you remember? Yeah, which means now we removed it from H4. Let's try that. A proton because the thing is that first we removed a proton and then sazo remove intoni a neutron where the proton was already removed. Now we remove the neutron straight from the original. That's the way I understand it. I think it should be. So now let's see. Yes. So we had this H4. Ne? So now we want to remove what? A neutron. So obviously we will be left with H. Will it not give us one of the answers there? Because now if you remove that, you're going to be left with 3 here. And then 1 here, 2 here. And then plus that one, which is 1, 1, maybe and 1. But something like that. So let's see. So we know that the mass defect will actually be the mass of what? Of H3, ne? Plus the mass of neutron minus the mass of helium itself, ne? Yeah, there's a sort of a difference in yabo. Because that time we removed the neutron while we had removed the hydrogen. So here it was 2, yabo. So now we still left with 3 here. So now from here we can take H3. See for H3 what did we have? According to this, our H3 is that 3.016049. 3.016049 U. Then we want the neutron. Neutron is 1.008665 U, right? I think there's Bambe's number as time goes on. I don't know, but they are not there in the question paper. That's all I know. But either way, miss, I think we need to know only 2. Because I think Khaswane did state that. I think we need to know for a neutron and a proton, that's it. Yes, because Vele, they are not there. So minus helium, and then our helium was that 4.002 something, I guess. The total one there, 4.002603. So that should be, where's this thing now where I wrote? Hey missed. This thing is problematic. Yabona, I don't see what I just wrote. Yeah, let's just go to another slide. So just gonna copy this because I know it does things like this sometimes. I just need to open a new one. So now Control V. So now we said we wanna remove what, a proton, I mean a neutron. So we said that, yeah, so we said that change in mass is equal to, now the mass will be left with H3, ne? Plus the mass of what, of that neutron, minus the mass of the helium itself. And then we said now the H3, that should be the 3.01649 plus 1.008665, which is the neutron, and then minus helium, which is 4.002, and then according to this is this one, 603. Let's see what do we get there, man. 3.01649 plus 1.008665 minus 4.002603. Then I get 0.02255 Then now calculate the binding energy. Will be equal to change in mc squared 0.02255 multiplied by 931.5, then times 931.5, I get 21.007 mega electron volt. So you see, this is the answer we get with. To start by removing a neutron there, get 21, because I think when we removed the hydrogen it was different. Let me check where we removed the hydrogen. Yeah, these things, something happened with the slide. So yeah, but I think that's it, man.